Good evening and welcome to tonight's Senior Connection program, How the Last Ice Age Still Shapes Our World, where we will learn about geology, glaciers, and climate change. The Senior Connection is a shared interest group sponsored by the Tufts University Office of Alumni Engagement. I'm Yvonne Bayevsky and I'm the program chair of the Senior Connection. We are creating programs for jumbos 55 and up, and of course, we enthusiastically welcome alumni and students of any age who are interested in joining us. Geology brings together many fields within science and mathematics to help us understand the world around us. Our speaker tonight is Professor Emeritus Jack Rich. Jack arrived in the Department of Geology at Tufts, now the Department of Earth and Climate Sciences, in 1985 after completing his undergraduate and graduate degrees at Lehigh and Syracuse universities. Jack is researching the history of glaciers in the northeastern U.S. with a focus on reconstructing glacial and climatic events of the last ice age from about 25,000 to 11,000 years ago. Since 2007, Jack has devoted much of his research to detailed field mapping and the dating of rock units north of Boston. He remains deeply engaged in fieldwork, often spending 4 to 5 days each week mapping the geology of the region north of Tufts from Winchester to Lynn. The audience is welcome to ask questions using the Q&A box below. Jack, thank you so much for joining us tonight.
Well, thank you very much. It's a real pleasure to be here and to talk to you all. I know that there's at least a few former students who have signed up for this. So what I hope to do tonight is to give you some sense of what it was like during the last glaciation and some of the side effects of glaciation that we don't often hear about. And so with that, what I'm going to do is I'm going to share the PowerPoint show. And you should be able to see it now. Can everybody see the show? Is that? Looks good. Okay, so you can see the show. There's at the end of this, or maybe in the next day or two, a PDF of the show is also going to be circulated because there's lots of links to the internet, and you can go explore things in further detail that I talk about. So hopefully you'll have an understanding of what ice ages were like. Okay, so now, there we go. Okay, so I guess the first thing we got to do is talk about what a glacier really is. It's simply a body of snow and ice. It forms by the accumulation of snow, and sometimes that snow melts and refreezes. But another important characteristic is that it has to show past or present self-movement. It either slides across the land surface or deforms or does both of those things. And here's a great example of a glacier that is moving. It almost looks like silly putty has been dropped on the land surface and is now spreading out. So glaciers today and in the past essentially occur as two types when we worry about their physiography and their shapes. So that first group is ice caps and ice sheets, and the two biggest ice caps or ice sheets on the planet today are in Greenland and in Antarctica. All ice caps or all glaciers owe their existence to snow being preserved at higher elevations or in the right climate conditions. And in the case of ice sheets, what happens is the glacier itself has a high enough elevation to produce the conditions that allow snow to continuously accumulate over time. So if we looked at that glacier in cross-section, here's the cross-section of the glacier. We've sliced it in half. And the center high point is what's known as the ice divide. And the snow and ice accumulates on the surface, and then it moves downward and it spreads out towards the margin. And we're looking at it in map view, that's what we call radial flow. So ice sheets have self-elevation and radial flow. They also have areas where there's net accumulation of snow. That's the accumulation zone or accumulation area. And then there are places where there's a net loss of material every year, and that is the ablation zone. Looking at that from above, it almost looks like a turtle on this diagram over here. So that's the first category. Here's a good example of an ice cap. This is the edge of the Greenland ice sheet, and I'll show you several pictures that were taken by a former professor at Tufts. This is Robert Nichols, who taught at Tufts from 1930 to 1969, and he took expeditions to Greenland and also Antarctica. This is the edge of the Greenland ice cap. If you were to walk up on the ice cap, you would walk 1,000 kilometers onto this, essentially as a white billiard table, all the way to the other side. So it's a big dome of ice. In some places in Greenland, the ice cap has formed over mountain ranges or in the center of Greenland, and the perimeter of Greenland is surrounded by mountain ranges, and it escapes through passes. And here's a good example in Northeast Greenland, an appropriate name for this glacier, the Elephant Foot Glacier. It's squeezing through a pass and out into a coastal plain. This ice that you see down here is frozen seawater. So those are the ice caps and ice sheets. The other type of glacier that occurs is what's known as a valley or alpine glacier. Looking at it in map view, what happens is snow and ice accumulates on a high elevation land surface, and it flows down slope into adjacent valleys. Tributaries merge with each other, and it flows down to lower elevations where it enters the ablation zone. So it also has an accumulation zone and ablation zone. The boundary between those zones is what's known as the equilibrium line, and there was also an equilibrium line on the ice caps that you saw previously. So flow in a valley glacier is confined to the valley, and the snow and ice form on a high elevation land surface. So these tend to be somewhat spectacular, and they're usually the glaciers that people visit because Greenland and Antarctica just aren't as accessible. Here's a satellite image that shows valley glaciers in the Himalayas. They're flowing to the north out of the mountains and also to the south out of the mountains. A lot of the glaciers on the south side look brown on the satellite image, and that's because they're covered with dirt and debris that has melted out of the glacier. So again, these long tributaries of ice join each other. And here's what it might look like on the land surface. This is flying over the margin of the Susitna Glacier in Alaska. And you can see the snow and ice accumulating at high elevation, and it flows down valleys. You can see tributaries joining. And down here is the ablation area. And you can see the debris starting to melt out of the glacier. There's another way to classify glaciers, and that's by their thermal regime or their temperature. So one type of glacier, which is usually what people visit, is a temperate or warm glacier. And what categorizes these glaciers, regardless of whether they're ice sheets or valley glaciers, is that their surfaces are pretty close to the melting temperature. And what I mean by that, probably within 10 degrees of the melting temperature. And they owe their existence to high snowfall. So they can be relatively warm, but because so much snow falls on the surface, they're able to sustain themselves. In the summer, the surface melts, and that produces lots of meltwater. And this is an example of a glacier. This is a picture I took in Alaska, and you can see the margin of the McLaren Glacier and lots of water that has come out of the glacier. So that's a characteristic of a temperate glacier. The other type of glacier is what's called a polar or cold glacier, and this is what the Antarctic ice sheet is. It's situated at the South Pole, and surface temperatures, mean annual surface temperatures, are at least down to minus 20 degrees centigrade. And these glaciers don't have to have a lot of snowfall. They can have very low snowfall. In fact, the center of the Antarctic ice sheet receives something like 15 centimeters a year. And so it is so cold that that's enough to sustain that glacier. There's very insignificant melting in the summer, and you don't see meltwater streams and rivers coming off of the glacier. So there's a small amount of melting. These glaciers are so cold that when they reach the coast, they can extend out over the ocean surface as what's called an ice shelf. Ice shelves go out onto continental shelves, and they're stabilized by high spots on the continental shelf where they rest, but seawater can still circulate in underneath them. And so these are sort of precarious, and this is one of the things that we worry about with climate change and warming ocean water in Antarctica. It will destabilize the ice shelves. If the ice shelves destabilize, the glacier behind it will start to flow more rapidly into the ocean. So what does this actually look like? Here's an example. This is the edge of the Ross Ice Shelf. There's a cliff face along the edge of the glacier, which extends well below sea level. So in some cases, this cliff face might be 150 feet high, but the cliff extends maybe down 800 or 900 feet below the ocean surface. So it's still a big slab of ice, and it's also very, very cold. So that gives you an idea of the types of glaciers that can exist. Now, there are also, in addition to the ice cap in Antarctica, there are also valley glaciers. And this is a map of a place called the Wright Valley in Antarctica. And this was a place that Bob Nichols, who taught in the department, took expeditions to back in the late 1950s, early 1960s. And when he got there, none of the glaciers had names. So what he did was he named the glaciers for his student assistants. And if you go to the Wright Valley today, you can see the Barkley and the Meserve and the Hart and the Goodspeed and the Denton glaciers, and those are all named for Tufts undergraduates. So a lot of Tufts history down in Antarctica. Here's a picture of those glaciers. This is a picture taken by Bob Nichols. The glacier here in the center, very narrow, and also moving very, very sluggishly and very slowly is the Meserve Glacier. So here's a former student. I'm not sure who that is. Here's the margin of the Meserve Glacier, another person here for scale. This is an extremely dry environment. And, you know, it would be like being in Death Valley or someplace like that, except it's very, very cold. So that gives you an idea of what's out there. So what is it like during a glaciation? And a glaciation is simply a period of time conducive to the development of glaciers. That's a fancy way of saying it's a colder climate. And what happens is there are many places where snow will begin to accumulate on the land surface. What we need to preserve that snow is, first of all, we need a land surface. You can't form a glacier out over the ocean, and you need either high latitudes or high elevations for that to occur. So they can form by excessively high snowfall. With warm temperatures, they can form in very cold climates that do not have a lot of snowfall. They're just so cold they will preserve the snowfall. So this is a map of what it was like during the last glaciation, and it shows at the maximum of the last glaciation, which was about 25,000 years ago, and it shows where glaciers accumulated on the planet. A couple of corrections here. You notice that there's a blue water body here. That's Hudson Bay, and that was completely covered by ice. And this is the Baltic Sea, the Gulf of Bothnia. It was also completely covered by ice. So we have mostly glaciers in the Northern Hemisphere. And in fact, over the last million years, when we've had a glaciation, when these big ice caps have grown, they've grown almost exclusively in the Northern Hemisphere. Why is that the case? Well, there is a land surface on which snow and ice can accumulate. If you go to the southern hemisphere at that same latitude, it is almost entirely ocean, and you just can't form large ice caps and ice sheets at that latitude. We also have mountain glaciers. So for instance, here in the Andes, places in the Rockies in the west, and various places in Asia, also in the Alps in Europe. You notice that there are these brown areas on the map, and these are places where, as a result of water being taken out of the ocean and piling up on the land surface, what has happened is sea level has dropped. And those are parts of the ocean floor that have been exposed by that drop in sea level. You'll also notice that Antarctica hasn't really changed very much from the last ice age to the present. And the reason for that is that the glaciers can't really extend very far out over the ocean, because what will happen is the ice shelves will break off and form icebergs if they get into water that is too deep. So that gives you an idea of what it was like. Here's a detailed view of what it was like in North America, where there were actually three ice sheets. The Laurentide ice sheet dominated the continent. The Cordilleran ice sheet formed over the Rockies and in southern Alaska, and they merged with the Greenland ice sheet. There was also a small ice cap over mountain ranges, the Brooks Range in northern Alaska. You'll also notice that there's a place in central Alaska that never had any glaciers, and the reason for that is that it was too dry during ice ages. Storms just simply couldn't penetrate that area and dump enough snow for glaciers to accumulate in that relatively low elevation area. So anyway, that's what North America looks like. The light green areas are places where the ocean floor is exposed during glaciation, and we'll come back to this area, which is the Bering Sea. So here's a map of that area. The land surface today is shown in a darker color, and the Bering Sea was high and dry. The passage between Siberia and Alaska is only 50 meters deep at its maximum. So if we take almost 130 meters of water out of the ocean to grow ice caps, that becomes a dry land surface and a land bridge between Asia and North America. So that existed till about 10,000 years ago and is a very important thing because it allowed humans to come into North America, as well as many different types of animals to be exchanged between these two continents. Here's what the situation looked like in Europe. There's an ice cap covering much of Northern Europe. The ice cap in Iceland is much bigger. And in the Ural Mountains, there's an ice cap covering the northern end of that mountain range. And then we have sprinkled around in other places where we have mountains, especially in the Alps and in the Caucasus. We have smaller glaciers which formed on the land surface. This map also shows how sea level changed. The dark green areas are places where the ocean floor was exposed. And you'll notice that the English Channel doesn't exist. It's a dry land surface, and you can walk back and forth from England to France at that time without getting your feet wet. So that gives you a clearer picture of what's going on in the Northern Hemisphere. There's another thing that happened. In Southeast Asia, what happens is sea level is lower, and all these light colored areas that you see here are exposed land surface. This is an animation, and it's running, and we're back to 19,000 years ago, and it's moving to the present. And what you're going to see is those areas slowly fill in with water. But this happens very slowly in the beginning. It's hardly noticeable until you get to about 12,000 years ago, and then you start to see that land surface invaded by rising sea level. And so we're at 13,000 years ago, and you're going to start to see some changes. By the time we get to 10,000, it'll be very different. And then at 7,000, it almost looks like it does today. And that was a period of very rapid sea level rise at the end of the last glaciation. And what's happening at that time is in North America, the ice cap is essentially disintegrating very rapidly. So we're at a point 7,000 years ago when the coastline looks pretty much like it does today because there's not much sea level rise left. And in fact, this thing up here says it's at -1 meter or so. So it's very much like today by about 4,000 or 5,000 years ago. So that's an interesting thing. Now, there's a red line on this map, and this is a line that was defined by Alfred Russel Wallace back in the 1800s. And Wallace is a person who very much understood evolution, and he almost beat Charles Darwin to the punch by publishing articles about the evolution. And he worked in Southeast Asia. And one of the things he noticed is that the animals over here to the right of the line are very different than the animals over here in the rest of Asia. And what's happened here is that the ocean is very deep, even during ice ages. And so there's no communication with land animals between those two places. So we have evolution going on to the right of the line very differently than it went on to the left of the line. So very interesting place. This is largely what is responsible for mammals in Australia evolving that are much different than in other places in the world. Okay, so I'm just going to flip to the next slide. So I want to tell you a little bit about my research. And I spent most of my time trying to understand glaciation in the Northeastern United States. I've worked over here in central New York, in the Mohawk Valley, in the Champlain Valley up here, in the Connecticut Valley, and in the Merrimack Valley. And what I've been trying to do is figure out the history of ice recession. So where was the front of the glacier as it receded and when? And you notice there are all these lines on the map. Some of them are colored, but they have numbers on them. And this tells you the age of that ice front position. And you can see how it retreats across the land surface. The heavy red line down here at the bottom is what we call ice maximum. So that's the maximum extent of the ice sheet. and then it receded into southern New England. And finally, we have a very detailed view when it recedes into central Connecticut and further north. So why is that the case? Why do we have this detailed image of deglaciation? Well, one of the reasons is that there are lots and lots of glacial lakes in New England. And glacial lakes have sediment in them that can be used to set up a chronology of deglaciation. So in the Northeast, there was a lake filling the Hudson Valley called Lake Albany, a huge lake in the Connecticut Valley called Lake Hitchcock, and then there was Lake Merrimack, and smaller lakes like Glacial Lake Winooski in Vermont, Lake Ashwellet near Keene, New Hampshire, and up here in the Champlain Valley was Lake Vermont, which was later replaced by marine water. So glacial lakes have sediment pouring into them. And in the summer, when the glacier is melting, lots of sediment pours in. And in the winter, what happens is fine sediment then settles to the floor of the lake. So in the summer, we have, lots of meltwater pouring in. We have strong bottom currents. And what it produces, and these are cores of that lake sediment, is these light colored layers that have a lot of silt and fine sand in them. And then winter comes along and the currents drop off and the lake becomes very still and it allows clay to settle. And those are the dark layers. So these are cores that were split and prepared for photography. And the reason there's such a great contrast is that we let them partially dry, and the sand and silt layers dry out faster and become lighter than the clay layers, which are still dark. So the two cores on the left are from Connecticut and from Glacial Lake Hitchcock, and this core on the right is from southwestern New Hampshire, Westmoreland, New Hampshire. So these are very valuable. You can count the number of years a lake was in existence, but you can also measure the thicknesses of these layers, which are called varves. And the thicknesses represent the history of weather in the area. So if you have summer where there's lots of melting and lots of sediment pouring in, you'll get a thicker varve. And the opposite is true when you have a relatively warm or relatively cool summer. So we can measure the thicknesses of all these things and put together what are called varve records. And it's possible to match these records not only within the same lake, but within different lakes. So we can come up with a long chronology of what was going on. So here's an example. Here are two plots of varve records, and they're plotted from older at the left to younger at the right. And this shows 1 century, and it shows the correlation between a record in the Connecticut Valley in southern Vermont and the Merrimack Valley further east at Concord, New Hampshire. And you notice that the peaks and troughs match each other. They're not perfect, but they match each other. And this is like a fingerprint for this time period in New England. So we matched lots of records together, and what we can do is produce a chronology. And I spent a lot of time putting these records together with lots of student projects, and what we have today is a chronology that's over 5,600 years long, and it starts down here. This is green stripes that you see here. Arbitrarily starts at the year 2700, and that was established by a person back in the 1920s, Ernst Antevs, who was a Swedish geologist who came over here and measured varves and started this whole process off. So this represents correlation of varves in the Hudson Valley, Connecticut Valley, Merrimack Valley, and then from Glacial Lake Winooski and Lake Ashwellet in southern New Hampshire. There are other varve sequences down here in southern New England and New Jersey, but they just haven't been hooked up to the main sequence in New England. So that's very useful. That's a chronology. And the critical thing about this in terms of deglaciation is that there are many places where we find a varve record and we measure varves and we find the bottom of the section resting on glacial sediment. And this is a type of glacial sediment called till. And that's the basal varve. That varve represents the year in which the ice receded from that position. And we have lots of those. So what we can do is plot their positions from south over here on the horizontal axis to north, and their arbitrary year in the varve chronology. And what that does is it ends up giving us a plot of where and when the ice receded. We call that a time distance plot. So we can also get the rate of deglaciation, how fast the ice was receding. And one of the surprises was that up in New Hampshire and Vermont, in this area right here on the map, the ice receded at 300 meters per year, which is extremely fast. And summers must have been quite toasty at that time in New England to allow the ice sheet to recede that fast. At the same time, we have episodes where that recession is halted and the ice actually readvances a little bit. So that's actually happening up in here in northern New England near Littleton, New Hampshire, and in a couple of other places. So that gives us the history of deglaciation and allows us to draw lines on the map for certain places where the glacier halted. It may have built a deposit called a moraine, or it may have just hung out there for a while and not continued to recede. So what those episodes are sudden periods of cold climate that allow the glacier to sort of stabilize or re-advance. All right, so we've done that in New England, but we haven't really been able to do that over in New York State, except you see all these lines. Well, we have all of these end moraines and deposits that tell us where the margin of the glacier was at one time. What we can do is look at the varves that occur in this area, and although we don't have a chronology, we can take oriented samples of the varves in New York and oriented samples of the varves in the Connecticut Valley and measure magnetic directions. And what happens is through time, magnetic directions change. So if you've ever used a compass for orienteering, you know that the compass needle doesn't point to true north, it points to magnetic north. And the position of magnetic north changes over time. And we can use the record from the Connecticut Valley, correlate it to the record in New York State, and figure out which end moraines or ice margins over here are the same as those in New England. And you see numbers applied to the ice margins. So we have a very detailed view of what was happening. A new colleague of mine at Tufts is Allie Balter Kennedy, and she specializes in a new dating technique called cosmogenic dating, where she measures on surfaces that have been scraped off by the ice the buildup of beryllium-10 isotopes, which are caused by cosmic ray bombardment of the land surface. So after the ice recedes, that land surface, which has been cleaned off by the glacier, starts to get bombarded again, and beryllium-10 builds up, and we use that as a clock. And she now has lots of ages for ice margins down here, from the maximum extent back to where we have lake deposits that we can use to figure out the history of deglaciation. So that's the story in New England, and this can be done in other places as long as you have glacial lakes or you have cosmogenic ages. Okay, so what I want to also do is tell you about some of the consequences of glaciation. Some things you may not realize have, happened in the past, and one of the things that happens is anytime you put a weight on the crust, what happens is the crust starts to depress, and we call this type of depression or balance between the weight of the crust and the underlying mantle isostatic depression. And so the arrows on this diagram, which is a cross-section of the Antarctic ice sheet, show the relative amount of depression that the land surface has experienced. So there's more depression over here where the ice sheet is thick, and there's less depression out here near the coast where the ice sheet is thinner. So the land surface gets depressed. The ice shelves don't depress the land surface because they're no different than having the ocean on the land surface. That ice is buoyant. So what happens is that the ice flows onto the land surface during a glaciation. It depresses the crust, and then when the ice recedes, the land surface rebounds. So we call that isostatic rebound or isostatic uplift. But it doesn't happen right away. So that is a very useful thing. This isn't only true of glaciers, but large water bodies can do this, like big lakes can do this. So the map on the left shows what the southwestern United States looked like during the last glaciation. And you notice there are all these big lakes. And the reason for that is we have all these closed basins, and there's runoff from the mountain ranges, and there's not as much evaporation during the last ice age. So water begins to fill up in these basins until it finds a drainage outlet. And I'd like to draw your attention to this basin right here. This is the Great Salt Lake, shown in light blue. And the darker blue is a lake called Lake Bonneville, which filled up this basin 700 feet higher than the Great Salt Lake until it actually drained northward out this outlet right here to the Snake River Valley. So 700 feet of water on the surface of the crust over this surface area causes isostatic depression. So when the lake's in existence and the crust is depressed, a shoreline forms around the margin of the lake. So here's what one of those shorelines actually looks like. This is the place I take my students to when we go on the Death Valley field trip. And you can see the highest lake level was right here. It's like a bathtub ring around the lake basin. And then as the lake begins to recede, it leaves smaller shorelines. And we can go out and measure the elevation of that shoreline and put together what the lake looked like when it was in existence. But it's dry, it's completely gone. This is in Trona, California. This is the shoreline of what's called Searles Lake. Okay, so shorelines formed on Lake Bonneville. And then what happens is the lake evaporates or goes away as the climate warms up and the crust rebounds. And what it does is it takes the shorelines to a higher elevation. It takes them to a higher elevation in the center than it does along the margins because the water was thicker in the center and the weight was greater. And that's what's shown here on the right. The contour lines that you see here are showing the elevation of the shorelines of Lake Bonneville. Out here along the margin, they're down at 1,570 meters, while out in the center of the basin, the shorelines on some islands are up at 1,620 meters. So there's a 50-meter difference in the elevation of the shoreline as you go across the basin, and then it comes down on the other side. So that's one of the side effects of putting a weight on the crust. All right. So what actually happens is, you have a glacier invade the land surface. So let's say this is New England or someplace like that, and the ice is advancing from left to right, and it reaches its margin, and the area under the glacier is depressed more where the ice is thicker. And what happens is material down in the mantle, which is kind of squishy, it's not molten, but it's squishy, it begins to squeeze out from underneath the ice. And that will actually cause the crust to bulge out in front of the glacier, what we call a peripheral bulge. Now, I'm going to show you diagrams like this, but these things aren't that accurate. And the way that they aren't that accurate is that they're hugely exaggerated in the vertical scale. Okay, so what I thought I would do to show you what that looks like is here, down here is a diagram showing the crust of the earth on top of the mantle, and that thin white slice that you see there is the glacier laying on the land surface, except even there, it's shown 2 times too thick. So we're dealing with a very subtle response to the ice being on the land surface. So let's say that we start with a horizontal surface, the red dashed line, and this is what the shape of the crust would look like with that horizontal surface, to be depressed over here, and it would bulge upwards out here in front of the ice sheet. Okay, so this is something that we actually see on the Tufts campus. And we can go back to about 17,000 years ago when the ice sheet finally receded from this area. And as the ice recedes, it leaves this area and it doesn't rebound right away. It's slightly delayed, and it takes a while for the mantle to get its act together and for it to squeeze back underneath where the ice sheet was. So what you're seeing here, this yellow line represents where the land surface is 17,000 years ago, and the blue line represents where sea level is at that time. It is 100 meters below where it is today, and it still makes a shoreline on the land surface. Those red dots represent a beach. It would probably be a beach with lots of boulders because the waves are cutting into glacial sediment, and you see lots of boulders and everything being left behind. So that's at 17,000 years ago, and what starts to happen is that the land surface starts to uplift. It uplifts before sea level really has a chance to change in any important way. And then later in time, what happens is sea level rises, okay? And the sea level comes up to its present position, and lo and behold, that strand line that we formed 17,000 years ago is left high and dry, and it's actually 15 meters above sea level in the area of the Tufts campus, which means that it crosses right through campus. Okay, so I'm going to show you where that is. And this is a map of the campus. Here is the library. This is Cousin's gym over here and athletic fields, which were a brickyard. And the blue heavy line is the shoreline that formed on the Tufts campus immediately after ice receded. And you notice that over here at Anderson Hall, the engineers have, a shorefront property, and that explains why the hill is so steep over here at the memorial steps. It was undercut by waves, and that made it was essentially a cliff face at that time. We can trace the shoreline around. The Ellis Oval is completely under marine water across from the gym. There are clay deposits, and before the university bought that land, there was a brickyard there, and they were cutting clay and firing the clay to make bricks. The shoreline up here, parallel to College Avenue. Eventually, we get to an intersection of College and George Street. And what we're going to do is go up here and take a left, come down George Street, and look back at campus on this street right here. This is Hume Avenue. And so that's what you see right here. So we're on George Street. We're looking back towards campus. The campus is up here. But you notice that there's this gentle slope right here. And all of a sudden, the land surface goes up. And that's the wave-cut scarp that's on the land surface from the ocean at that time. So there's lots of features around from glaciation. This is an unfired brick from the brickyard that was across from Cousin's gym. And if we found shells in that material, here are some of the species or different shell types that we would find. We would not find these shells today in Boston Harbor. They live in very cold Arctic water, and to find these same species today, we'd have to go to northern Greenland or Canada to find them in ocean water. The clay that forms in this area and these shells is what's known as the Boston blue clay. So anyway, that's some of the history of our campus. So, whoops, sorry about that. So we have this situation where the glacier can recede, and then normal things start to happen on the land surface, probably in a tundra type environment. So let's say that we do the same thing, except that we have a tilted land surface like this. Let's say there's a river flowing down the land surface, and before the glacier arrives, that river easily drains to the, but we put a glacier on the land surface, and what happens is this yellow line down here is the original position of the land surface. The land surface is depressed underneath the glacier, and out here is the peripheral bulge. And so you notice that a river trying to flow on this surface right here after the glacier recedes can't really make its way over the bulge unless it's a really steep land surface. So what happens here is a lake is going to have to form before the water can actually drain over the bulge. Well, there is one place in the northeastern US where that actually happened. This is the Delaware River right here between New Jersey and Pennsylvania. And it drains, here's the edge of the ice sheet, this heavy black line. The other black line is actually the edge of another glaciation, not just the last one. And the same thing happened during that event. And so the Delaware River drains away from the ice. It comes down here, and then what happens is it encounters the peripheral bulge. The red represents a small lake that was impounded in Trenton, New Jersey, but the water has no escape except it can flow over a divide out of that lake and into what's called the Millstone River and out to the ocean just south of Staten Island in New York. So very different drainage pattern as a result of the tilt of the crust in this area. The gray areas are other glacial lakes that I've worked on, and I've worked on this with a whole bunch of colleagues, and we're figuring out the tilt of these lakes and everything, and how much isostatic depression or tilting has occurred on the land surface. So that's one of the effects of tilting the land surface. So this same situation is still affecting Boston, okay? So the crust was depressed, it had the ice sheet on it, and that's shown by the orange, and there's a peripheral bulge. But when the ice leaves and the land surface has had enough time to recover or to rebound, we're going to get areas that were well back under the ice sheet that are still uplifting today. And the peripheral bulge doesn't just collapse, but it migrates inland. So the blue line shows what this orange area might look like after a substantial recovery. And today, what's left of the peripheral bulge is under Boston. And that area is still subsiding or sinking. So that means that Boston has a real sea level change problem. Not only is sea level going up, but the crust in Boston is going down about a millimeter to a millimeter and a half a year as a result of the collapse of the peripheral bulge. And so we have to remember that when we're trying to measure sea level, that there's a couple of different causes for relative sea level changes. This area up here is interesting. If we go far enough inland, so for instance, at Hudson Bay in Canada, we can still expect to see some uplift going on. Before we go there, there were questions before this about subsidence. Subsidence can be caused by, isostatic adjustment. It can be caused tectonically. But another thing that can cause subsidence or the sinking of the land surface is human activity. And in the Central Valley of California, in the San Joaquin Valley, there's been a lot of pumping of groundwater. And what the USGS does is they keep track of the elevation of the land surface. And the pumping of the groundwater has allowed the collapse or the compaction of the sediment in the subsurface. So this picture was taken in 1977, and here's the land surface in 1977, but here's where 1955 as a result of subsidence. Here's another area in San Valley. Here's where it was in 1988. Here's where it was in 2016. And the USGS has maps to show how much subsidence has occurred in this area. And this is all because of pumping of groundwater for irrigation in that Central Valley in California. The pump oil and gas can also do this and leave, or cause subsidence to occur. Okay, so let's just go back to the glacial world, and we're going to go to a place like over here where the crust is still uplifting, and that's Hudson Bay. And the crust is still uplifting at a rate of about 3.5 meters per century. So that means in your lifetime, you would see a pretty substantial sea level change, over 2.5 meters of sea level change, which is astronomically high as compared to what we're seeing in Boston or someplace. And when you look at the shoreline of southern Hudson Bay, you see all these ancient shorelines, and what's happening is the land surface is lifting and leaving the shorelines high and dry. So it's the modern one forming right here. And we shorelines because they have shells in them, and we can radiocarbon date them and figure exactly how old they are. Okay, so another place where this is happening is in Scandinavia. So the Baltic Sea and the Gulf of Bothnia are uplifting still today. Now, that's an important thing for archaeologists to know, because the shoreline that you see here was in existence back, 1,200 years ago when the Vikings were in this area, and they also built docks. So when archaeologists find those docks today, they are no longer at sea level. They have uplifted. And in the center of where the ice sheet was, it's as much as 9 millimeters a year. And that makes the docks unusable today. So you have to understand that to really understand the archaeological record of what's going on. Anyway, so that's glacial isostases. So the last bit of this talk, I wanted to talk about something that's really fun. I find this just absolutely fascinating, is this to animals on the land surface during ice ages. And there's major things that occurred. Now, we've had major ice ages back for at least 1 million years, and then there were climate fluctuations, maybe not as severe, but very frequently back to about 2.5 million years. So the last glaciation isn't really the only glaciation that has existed. And through all of those events, the animals that live on the land surface have to adjust because the climate cools off, plants start to migrate, and these animals have to, keep up with their food source. And so they're constantly migrating back and forth across the land surface as the climate oscillates between ice ages and interglacial periods like we have right now. So migrations are important. The other thing that's important is at the end of the last ice age, and not the other ice ages, we had this extinction event of megafauna, large mammals, and especially in North America and a little earlier in Europe, we had mammals going extinct. And one of the prime examples is this mammal right here. This is a woolly mammoth, or Mammuthus primigenius. So these lived along the edge of the ice sheet, and they're very large. I'll show you an example of one of these things in a second here. And almost all of them went extinct at the end of the last ice age, about 11 to 10,000 years ago, except for a small group that was isolated on Wrangell Island in Alaska. And on that island, these creatures developed into a pygmy race of mammoths. Some of them were only about 4 feet high at the shoulder. This same sort of thing happened in the Mediterranean Sea and also on the Channel Islands off of the coast of California. So we get these really small individuals forming, and it's not an uncommon thing when large animals are isolated on an island, they turn into, a smaller version of themselves. So they actually went extinct 4,000 years ago. That's the time when humans arrived on Wrangell Island. So why did these distinctions occur? So there's two leading ideas. One is climate change at the end of the last ice age was very abrupt and erratic. And that's also true for other ice ages. But we also know that humans entered North America, and for the first time, the large animals in North America could have been hunted. So we think that, both of those things probably influence it. We don't know whether human hunting primarily responsible. We don't really think that climate is entirely responsible because they survived other ice ages without any problem. So that's a woolly mammoth. So a big pachyderm. There were other pachyderms that lived in North America. This is also a mammoth. It's called the Columbian mammoth. It was originally named Mammuthus jeffersoni because Thomas Jefferson was fascinated by these things, and he collected as many skeletons and bones of these extinct mammals as he could. And at one point in the past, this Columbian mammoth was called Jefferson's mammoth. So these lived a little bit further south, not up against the ice sheet, but across the southern United States and in California and places like that. And this is a mastodon. And these were very common here in the northeastern US and across the edge of the ice sheet. And their skeletons are probably more common than either of the mammoths, especially in the Northeast. So we had these animals all going extinct at about the same time, between about 10 and 12,000 years ago. A pachyderm that often gets overlooked and went extinct in South America only about 6,000 years ago is something called a gomphothere. And it looks very much like a modern elephant, except it has 4 tusks on it. So we have some very unusual animals here. Here's some examples of these pachyderms. This is in the American Museum of Natural History in New York. This is a mammoth. I'm not sure if it's a Columbian mammoth or a woolly mammoth, but I think it's probably a Columbian mammoth. You can see it's a very large animal. This is a mastodon right here, and it's hard to see, but right in the background here is one of those gomphotheres. So just one of the strangest fossil sites is in Nebraska, where 2 male Columbian mammoths locked their tusks together and they couldn't get apart. And they finally fell over. And when they fell over, they fell on a coyote and crushed it. And the fossil site has these 2 mammoths and also a coyote skeleton preserved. The 2 Pleistocene elephants that inhabited much of North America, the mastodons and the mammoths, had very different structures. This is the tooth of a mastodon, which was made for browsing and crushing. And this is the molar or tooth of a mammoth, which has a grinding surface on it. So they're very different. And if you go back in time, their closest common ancestor is at least 5.5 million years ago. So these fossils are found all over the eastern United States, from Florida all the way up to the Northeast, where we had glaciation. So this includes mammoths and mastodons. And you notice after the ice receded, mammoths and mastodons inhabited the land surface as far north as about where Boston is. And it was approximately that time that they went extinct here in the Northeast. And so you even find them out in the continental shelf. And fishermen dredge these things up occasionally. There's a local mastodon tusk that was recovered from Spy Pond in Arlington, and there's a newspaper article here. You can look it up and read about it. So these are animals have also entered our culture and our art. Charles Wilson Peale actually made a painting called The Exhumation of the Mastodon. And this is the discovery of a mastodon and the excavation of that fossil in Hudson Valley. So they weren't the only mammals that went extinct. In North America, there was something called the American lion, which is shown down here. It lived in central Alaska during the last ice age, and we've also recovered fossils of this thing across the 48 states. It was about 30% larger than an African lion. And then there were also these saber-toothed cats. There's several different species. This one here is called Smilodon, and 2,500 fully preserved skeletons of this have been found in the Rancho La Brea tar pits in Los Angeles. So these were predators, and another animal that we can sometimes find. Fossils of it are several species of giant bison. This is a longhorn giant bison, which lived in the Yukon Valley in Alaska. And back in the 1970s, an almost complete body of one of these things was found frozen in the tundra in a gold mining operation. And this thing had been killed by an American lion. The tooth marks were on its nose and everything. And that's precisely what I know this isn't great to look at, but this is precisely what happens in Africa with African lions trying to kill buffalo. And one of the teeth of the lion is actually embedded in the skull of the fossil. But the fossil isn't just a skeleton. The whole body is preserved, its organs and its hair and everything. And we know quite a bit about this organism. There are seeds in the stomach of this thing, and when they thawed them out, they actually germinated. So this is 40,000 years old, frozen in the permafrost in Alaska. So interesting things happening. There were native horses in North America. They were more closely related to zebras. The wild horses that we have today were released by Spanish explorers in the 1500s, and they have nothing to do with the species whatsoever. The species went extinct, again, at the end of the Pleistocene, 12 to 10,000 years ago. There were also bears that went extinct at the end of the Ice Age. In North America was a thing called the short-faced bear, which had very long legs and probably ran down its prey. And in Europe is something called the cave bear, which luckily, it's because it's huge, was a vegetarian. And it lived across Europe and Asia. And as far as we know, it did not live in North America. And then there's some really weird animals. In Europe is a woolly rhino. And we find fossils of those in the British Isles all the way across Siberia. And in North America and South America are some really strange animals. These are glyptodons, which are like giant armadillos. And then there were giant ground sloths. This is Harlan's ground sloth. One of these ground sloths, I'm not sure whether it's Harlan's or not, when it stood up on its hind legs was 18 feet tall and a very big animal. The glyptodons were as much as 450 pounds. And this is again in the American Museum of Natural History. Here's a skeleton of one of these giant ground sloths. And here's a glyptodon. This is a modern armadillo down here for comparison. And perhaps the weirdest of these animals is the giant Pleistocene beaver. Here's a modern beaver for scale. It weighed about 440 pounds and it was 9 feet long from nose to tail. So that's the tale of the last ice age and lots of weird things. I could tell you a whole bunch more things about, the ice age and how things were different. But so that's the end, and I'd be very happy to take questions if people have them. And I guess I'll stop the share right here so that we can have questions. Is that correct?
I have a few questions for you.
Okay.
Great. So first off, using USGS topo maps, someone would like to know where the shoreline of Glacier Lake Concord was.
Glacial Lake Concord. Okay. There's actually a geologic map for that area. The Concord Quadrangle, which has the lake, A friend of mine named Carl Kotef, back in it might have been the 1970s, made a geologic map of that area. It's called a superficial geologic map, and it shows where all the deposits and where the shoreline of the lake would have been. So Lake Concord wasn't a very big lake. It didn't have big waves on it, and it doesn't have. I doubt you'll find a shoreline, but you can find deposits of sand and gravel that were dumped into the lake from rivers or from the margin of the glacier. And there are big deltas. So, for instance, if you go to Walden Pond, which is where an ice block was surrounded by a delta, you can actually see the flat surface at the top above the pond, which is the delta surface. And when the ice block melted out, it left the pond behind. So if you go online and you look up superficial geology Concord quadrangle, you'll find a PDF. I'm sure you'll find a PDF of that geologic map.
Great. Why are the ends of temperature glaciers covered with gravel or rock? Is there
So
internal ice flow turbulence that brings bottom debris to the top, or are we just seeing terminal moraine with surface that slopes smoothly into the ice of the glacier?
So the debris that you see on the glacier is actually very common in valley glaciers because where valley tributaries join, they trap debris, rock debris. And that's what those stripes were on the surface of the glacier. Those are medial moraines. But the bottom of the glacier can often freeze sediment on. And near the margin of the glacier, that starts to melt out where that bottom part of the glacier is exposed. So it makes it very dirty. It can actually be very, very muddy. And what really determines how much sediment is on the surface of the glacier is how thick that material is that was frozen in on the bottom, and also how many medial moraines have melted out on the surface.
For one of our attendees, they said one of their neighbors was a scientist at NSF and said that the melt rate of Greenland glaciers are likely to accelerate because as the meltwater seeps into surface crevices during the summer, will transfer heat deeper into the glacier. In some cases, the meltwater will reach the underlying bedrock, and that would reduce friction between ice and the bedrock. If that happens, the glaciers are likely to move rapidly toward the coastline. Is that correct?
Yeah, that is correct. And in fact, what's happening on the Greenland ice cap today, and we started to notice this beginning back in about 1995 or so, is that melting is so extreme that big pools of water will actually form on the glacier up near the equilibrium line where there's not a lot of slope. And those pools of water get deep enough so that if there's any crack in the glacier surface, the water pressure will actually start to force the crack open, and that water can drain and it can flush like a toilet flushing all the way to the base of the glacier. And because ice is buoyant and it floats in water, when the water gets to the bottom, it lifts the glacier off its bed and friction is reduced and it begins to slide very rapidly. And so that's happening today, and this has been well recorded. And this happens in a lot of places where the glaciers are flowing to a fjord, and you get a huge discharge of ice into the fjord. Some fjord glaciers in Alaska are flowing at excessively high rates. There's one that flows at something like 9,000 meters a year. So it's just really whipping along. You can almost see it moving in that case. So that's largely because of water buildup at the base of the glacier that's happening, and that's going to continue to happen as water goes to the bottom. More important than the temperature of the water is the fact that the bottom's getting lubricated and lifted off its bed by that activity.
Great. Thank you so much, Marie. I'm going to turn it over to you. Thank you so much, Jack.
Yeah, sure. If anybody would like to ask a question, they can email me. I'd be glad to answer emails about it. I hope I'm not opening myself up here, but I'd be glad to answer questions, and I can direct you to newspaper articles or pictures that will demonstrate some of these things. Too bad I don't have a picture right handy of those melt pools on the Greenland ice cap surface.
Thank you, Jack, for being with us this evening and for bringing clarity to a complicated yet fascinating topic. I'm Marie Pareto-Hedin, president of the Tufts Senior Connection. I also want to thank the staffs of the Office of Alumni Engagement and Tufts Technical Services for making this program possible. We are so grateful for our partnership. And a big thank you to you, our audience, for being with us. If you are interested in learning more about the Tufts Senior Connection, please contact Karen McCauley or Rachel Shaw. If your class year ends in a 1 or a 6, your reunion is coming up. May 15 through 17 are the dates for the 30th and 70th classes, and May 29 through 31 for the 1st through 25th classes. On May 15th, we also have the 55 and over lunch on campus, which is great fun. If you have any questions, you can contact Karen McCauley. The board of the Senior Connection is currently working on several exciting in-person and virtual programs. Please watch for future emails with details including registration information. This concludes our program. Have a wonderful evening.